So now in section S2, we're going to talk about some advanced power flow techniques using PowerWorld Simulator. So we're going to get into more detail of solving power flow solutions in Simulator itself and telling you how it solves them and where a lot of the various pieces of a low flow solution are handled and where they come from in Simulator. So an overview of what we're going to talk about is we're going to give you an idea of how an actual single solution is processed in Simulator. Sometimes people misunderstand the term single solution. They think that means just the Newton-Raphson part of the low flow solution. That is not a single solution in Simulator. There's actually several parts to a single solution in Simulator, which involve a pre-processing step, a megawatt control loop, a voltage control loop, and then the inner power flow loop, which is actually where the Newton-Raphson itself occurs, is in the inner power flow loop. There's other things that go on outside of that, all of them iterative and all of them combined to come up with a total solution that balances the power flow equations, the generation megawatt control, the voltage control from generators and transformers and switch shunts, and so on. There is actually a complex process that goes into it, and I will describe that here as well. We'll also talk about some advanced options for a power flow solution and how you can set up the options in Simulator to adjust what your power flow solution does. There's also some area control topics that we'll talk about with multiple islands, and some solution diagnosis aids when you're looking at a low flow solution and trying to figure out what it's doing or why it might not be solving and what you can do. So what does it mean to do a single solution in Simulator? And again, we don't want you to confuse this with a single Newton-Raphson or other technique power flow. A single solution in Simulator is more than that. There are actually 3 nested loops that iterate between a power flow routine, logic to control device switching, and generation control until the power flow is solved and no more device switching is detected. So there's several different stages or levels to the iteration. An overview of that single solution routine is there initially will be a pre-processing step. That pre-processing step involves things like angle smoothing, which angle smoothing means if you close in a line, we try to approximate what the change in angles will be across the line so that there's not a large angle difference when you try to solve the power flow. That can result in the power flow solution failure if that angle difference is too big. So there's some angle smoothing routines. There's generator remote regulation viability routines that check to make sure that a generator that is designated to regulate a remote bus actually has a path to regulate or provide VARs to that bus. If it does not, then we internally remove that generator's ability to regulate the remote bus and it will regulate its own terminal bus instead. And we also estimate megawatt changes needed if, for example, you have changed load and we're getting ready to solve the power flow. We will estimate what the generation output will approximately need to be to balance the load and apply it before we even do the solution, because we don't want a large difference between the load in the case and the generation in the case when you start trying to solve the power flow, because the power flow may fail to converge if the difference between the generation and load is too high. So given that we do those pre-processing steps, once we have that done, there's a 3-nested loop solution process. The inner power flow loop was what we talked about in section S1, the Newton-Raphson load flow. We traditionally call that the actual power flow solution. So that's where Newton-Raphson occurs. There's then a voltage control loop, or what we call the middle loop, which takes place outside of the inner loop and handles things like switching transformer taps and so on to maintain voltages. And then we have the outer or megawatt control loop. That loop is responsible for determining if generation needs to be changed in order to meet load or changes in interchange, or to follow whatever type of generation control the generators have been, or the areas that the generators are contained in has been set to solve. It could be optimal power flow, it could be participation factor, AGC, it could be economic dispatch, or something of that type. So now we'll talk about pre-processing a little bit. What is angle smoothing? Again, we want to reduce large angle differences across elements that have recently been closed to reduce the initial power flow mismatch. If disabled, closing a line with a large angle difference often causes the power flow to diverge, and we want to avoid that. Angle smoothing also works for a series of branches that are close together. So out west, for example, where you have your multi-section lines, all those lines typically close in or out together. So angle smoothing will work across all of those series of lines to try and make sure that the angle difference is minimized for each section so that we can have a solution that is attainable when we solve the power flow. Following a topology change, simulator also adjusts zero magnitude voltages in groups of buses connected by low impedance branches. So in other words, if it closes in a bunch of buses and some of the buses have values of 0 and other buses nearby across low impedance branches have values that are non-zero, we will assume the buses that have 0 voltage should instead have the same voltage as the other buses nearby that are across the low impedance lines. Because again, if you start with a value of 0 for your starting point voltage, if you remember back to section 1 when we talked about bad initial guesses, typically starting with a guess of 0 for the voltage at a bus is a bad guess. You don't want to start there. So we do try to estimate what the value of voltage should be for a bus that's recently been closed in, and would start with typically a value of 0 because it was just closed, but we know that in reality it will end up with a value near its nominal, so we try to come up with what it should be before we even try and do a solution. So that is also a pre-processing step. When pre-processing the voltage profile of a solution before solving, we look at the grouping of the buses connected by low impedance lines. If a grouping of energized buses has a 0 voltage, other buses in the group do not, then the 0 voltage is changed to the first non-zero voltage found in the group. So that's what our starting point guess will be instead of 0. There's also a pre-processing step of checking generator remote regulation viability. It checks to make sure that a viable transmission path between a generator bus and its remotely regulated bus exists. If a generator has no transmission path, or if all possible transmission routes to the regulated bus are intercepted by other voltage-controlled buses, the generator is internally turned off of voltage regulation. So here you might see, for example, if these generators are regulating the voltage over here, but this bus tie is open, the only path it would have would be to go out through the system and come back. First of all, that's a long path, which means it would take a lot more VARs to regulate voltage. And secondly, there's more than likely other regulated buses that it would encounter along the way. And you cannot cross a bus that's being regulated by another generator in that path, or this generator has no way to regulate this bus. Therefore, we look for those things, and if we don't have a direct path, and we don't have a path that we can reach this bus without crossing another regulated bus, then we turn off the voltage regulation of these generators instead. So that is a pre-processing step, because we don't even want to get into simulator trying to solve for this situation when it's just not viable. So we check for that. We also like to do an estimation of megawatt change. So we store the initial output of the generators for reference during participation factor control, and then modifies the generator outputs in each area, super area or island, depending on what control is being used, to meet the approximate ACE requirements. So it's trying to initially come up with what the balance of generation equals load plus loss plus interchange should be. And then we do that by trying to prevent the slack bus from changing by drastic amounts during the first Newton-Raphson power flows calculation. Because if we don't make that approximation, and there's a big difference in some of the areas between its generation and its load demand and interchange, the first step of the Newton-Raphson iteration will apply a large chunk of that generation change to the system slack bus. What that typically does is cause solution failure, because the system slack bus goes to some output value that's way higher than the transmission system can actually transmit, and you get maximum power transfer exceeded. You're beyond the nose point of your PV and QV curves basically, and there's no solution at that point. So the load flow will fail. So we try to avoid those drastic changes by approximating the megawatt change prior to actually solving the load flow. So now let's talk about the 3 different loops of the iterative solution process. The megawatt control loop is the outer loop, and we repeat inside of that the voltage control loop and the change in generation and load to meet ACE requirements, and also the inner power flow loop is repeated. So basically the outer control loop contains the voltage controller loop and the inner power flow loop inside of it. And on top of that, it also checks the ACE requirements of each area and makes sure that generation is adjusted to meet the ACE requirements, or perhaps load as well, depending on what type of solution you're doing, because loads can be adjustable during the low flow solution if you're doing an optimal power flow, for example. They aren't often, but they can be. So it redispatches generation or load using the selected AGC control method for each area to balance this. So what happens in the middle, or rather the outer control loop, is it will repeat the voltage control loop, which itself repeats the inner power flow loop, and then also checks that the generation ACE requirements are met and adjusts generation if needed. And so it will continue to do that until no more generation and load changes are required. Again, for the OPF, it automatically respects the generator limits absolutely. For other types of control, like participation factor control, each individual generator has a field that will allow it to ignore its limits, and you can choose to do that, but just know that your final solution might result in it exceeding its limit. And again, you get back to the PV and the QV curve issue, you need to make sure that it doesn't go too high or it will exceed those critical values. So this is a description of the outer loop. Again, voltage control and inner power flow loop occur inside that, and then it does an assessment of the generation meeting the ACE requirements. If they're met, it stops. If they are not met, it adjusts the generation and then repeats. The voltage control switching loop and the inner power flow loop, internally then, they repeat the inner power flow loop itself, which is the Newton-Raphson load flow, and also internally inside that, any continuous switch shunts are also calculated as part of that inner power flow loop. We haven't talked about what a continuous SVC is. A continuous switch shunt is one that has dynamic output capability, meaning it can just calculate an exact value of VAR output for the switch shunt to regulate voltage. It's kind of similar to a generator VAR regulation at that point, but because it calculates an exact value of Q output from the shunt, it actually does that as part of the inner power flow loop. So it repeats the inner power flow loop, and then outside of that inner power flow loop, this switching loop does several things. It checks that generator megaVAR limits are enforced. If any are violated, then it's going to adjust the VAR limit of our outputs of those generators and redo the middle loop or the voltage control loop. It's going to check the DC line solution and make sure that it is balanced. If not, it will resolve and again repeat. It will see if any switch shunts need to change to a new output to keep voltage within range. It will check for discrete SVC switching. It will check for transformers that need to have their taps changed in order to bring the voltage back within range. And it will check any distributed fax devices and see if they need to be switched to bring their regulation back within range. If any one of these 6 things here is adjusted during one iteration of the voltage control loop, then it will do the adjustment and it will repeat the loop. So it will redo the inner power flow loop and resolve the Newton-Raphson power flow, and then check all of these things again until it gets to the point when no more controls are switched, or until a maximum number of control loop iterations is reached. And by default, it's 20. You can adjust that in the simulator options if you want it to be something higher or lower, but it will solve this inner loop and middle loop or voltage control loop repeatedly until none of these 6 things are adjusted, or until this maximum number of control loop iterations is reached. Once it reaches this point when it doesn't need to repeat the voltage control loop, it goes back out to the megawatt control loop, checks the generation, makes sure that no generation needs to be adjusted. If it does, it adjusts the generation and comes back and repeats this process potentially up to 20 times again. So there's where all the iteration comes on. And keep in mind that within this step 1 right here, the inner power flow loop itself is iterating, solving the Newton-Raphson load flow. So there's iteration going on here, there's iteration going on here, and potentially there's iteration going on here. So that's why we have 3 nested iterative loops solving the power flow. Now there are some options related to these loops. So for example, step 1, the inner power flow loop will repeat evaluating the mismatch at every bus. It will check the generator megavar output automatically and calculate it for the PV buses. It will calculate SVC megavars automatically for SVCs that are set to continuous. Optionally, it will enforce generator megavar limits at each step. Typically, we don't do that. However, there are rare occasions when that is necessary, and it's usually related to when you load a case that has generators that are already violating their VAR limits. Because if you don't check them immediately, it will try to solve the power flow with those VARs violating their limits first. If you instead check them immediately, it will actually try to move the VARs to within range first before it even tries to solve the power flow, and that might help you get to a solution, whereas leaving them outside their limits can cause problems. So we don't advise you checking that directly, but if you have trouble with a case solving when you first load it, and you notice that you have several generators whose VARs are violating limits when you first load the case, then you might want to check them immediately to try and help that. You can also optionally tell generators to only back off of VAR limits, and so you can say check back off immediately. Typically, if they're at a limit, it leaves them there initially and solves the case solves the bus as a PQ bus instead of a PV bus for the first time through the solution. But if you tell it to check if it can back off immediately, you can have it look and see immediately before it even does a solution if the VAR output at a limit could be reduced before you even solve it. That option, again, is not checked by default, but if you're having issues with it solving because the VAR limits the VARs are at limits and they shouldn't be, or it seems like they could be starting at something much less than that, go ahead and check that so that it can reduce them right off the bat, which might improve your ability to solve the power flow. And then it performs the power flow step, which is it solves Newton's method. By default, it's in rectangular form. There's also an option in simulator to do a decoupled power flow or to do the polar form of Newton's method. But by default, the most commonly used one is the rectangular Newton's method. And you do that until there's no mismatch. And you provide in the options of simulator what that mismatch tolerance is. And that's an MVA convergence tolerance that you provide. Our default is 0.1 MVA, and that's at every bus in the system. So we'll consider that the solution has been reached if the power flow in minus power flow out is less than or equal to 0.1 MVA at every bus. There's also a maximum number of iterations that you can apply that if it just doesn't reach a solution in this number of iterations, you can just have it stop. That doesn't always mean that the load flow was diverging, it just means that it was converging slowly in some situations. So sometimes if it stops at the maximum number of iterations, you can hit single solution immediately again and give it another 20 iterations and it may solve. Sometimes it goes to 100 and still tells you it can't solve. And typically if that's true, then there is something going on that is preventing the load flow from actually reaching a convergence. Okay, step 1A was continuous SVC limit check and discrete component switching. So in this step 1A, it checks that megavar limits on continuous SVCs, which are type SVS M01 and SVS M03. And then it switches any fixed shunts controlled by continuous SVCs, and then goes to step 1 if any SVCs or controlled fixed shunts moved. So within this inner power flow loop, there is this one check going on for these SVCs that are on continuous control, and if it determines any of those have to be adjusted, it just automatically adjusts them and redoes the inner power flow loop. before it even goes out and does any more of the voltage control checking. If these are met and the inner power flow loop has solved, then it jumps out to step 2, which is checking generator megavar limits. It backs off or enforces those limits and then checks for controller oscillation. There are situations where we see generators that oscillate back and forth. We have in simulator an option that you can check to prevent controller oscillation, which then means that if simulator detects a device like a generator toggling back and forth between the same value more than 2 or 3 times, I think it's 3 times, it will turn off the control of that device and move on, because otherwise you get stuck in a never-ending loop of that device toggling back and forth and you don't get to your solution. And then it updates the mismatch and voltage vectors and incorporates voltage vector changes by processing each generator. Then it goes on to step 3, which is solving DC line equations. We'll talk about DC lines later, but the power flow solution, they just look like a fixed megawatt injection and megavar injection that is a function of the AC line terminal voltages. So the DC lines are solved kind of as their own DC network, and then whatever their real and reactive power injection or absorption are at either end are applied as fixed injections at the terminals at the AC lines, or AC bus terminals. For the switch shunt control, we check the regulated buses for voltage limit violations and adjust the switch shunts appropriately. We also can control the total VAR output of generators by controlling the voltage at a particular bus. This is good for modeling a shunt that maintains VAR reserves. Shunts are adjusted one at a time, with each shunt only considering its own impact on the regulated bus voltage. The interaction between different shunts is not modeled here. Then it checks for controller oscillations and makes sure that switch shunts that appear to be oscillating are internally set off of control for the rest of the solution process. And then it updates the mismatch and voltage vectors for any changes that were made. Then we go to step 5, which is discrete SVC control. Only SVCs that are discrete type are switched in this step, so SVS MO2. This checks regulated buses, again, for voltage limit violations and adjusts the SVC control appropriately. Any fixed shunts controlled by the SVC are adjusted in this step, and SVCs are adjusted one at a time, with each SVC considering only its own impact on the regulated bus voltage. Again, interaction between different SVCs is not modeled here. And then we check for controller oscillations again and turn off any that are oscillating, and then update the mismatch and voltage vector for any changes to the SVCs. For transformer switching, now we check for the regulated voltages and megavar flows and megawatt flows for limit violations and adjust transformer controls in a manner dependent on the transformer stepping methodology, so a little different with transformers. If transformers are designated in the options to use coordinated sensitivities, then the tap change calculation requires a construction and factorization of a full matrix dimensioned by the number of transformers that need to be switched. Normally, this is only good for a small number when a small number of transformers needs to change. What this relates to is that when you change the tap on one transformer, it changes the impact another transformer may have on a bus nearby or whatever it's regulating. So there is a coordination of the sensitivities in this step. So if you use coordinated sensitivities and there's a small number of transformers that need to be switched, it will construct this matrix of interactive sensitivities between transformers and figure out how to switch them based on how each transformer will also affect the other transformer's ability to regulate. However, there's also a self-sensitivity only check where each transformer does not consider how it affects other transformers. It's much faster but maybe less accurate and may lead to more iterations before you reach where all the transformers are satisfying their regulation. Note, internally in simulator, we automatically take any situation where there's more than 50 transformers that have to change tap and do a self-sensitivity only, regardless of how you have the stepping methodology defined. And that's simply because it would take way too long to construct a large full matrix that we have to then operate on every single element of the matrix to determine how each transformer affects all the other transformers and come up with the best solution for all of them. If you're modeling large systems, you can still use coordinated sensitivities, but just recognize probably the first several iterations of your solution, it's going to automatically do a self-sensitivity only, because there's probably going to be, at least initially, more than 50 transformers that change tap, depending on what the initial condition of the case is. It also checks then for controller oscillations of transformers that appear to be oscillating between the same settings on the transformer, and will turn them off for the rest of the solution process, and then updates the mismatch and voltage vectors according to the changes of the transformer taps. And then the last step is step 7, which is DFACs, or distributed fax control devices. They attempt to keep the current on a branch within a specified range. The impedance of DFACs is modified to adjust the current. If the DFACs appears to be oscillating between control settings, then they are turned off of control, and the Y bus is updated with the new impedance values if the DFACs are adjusted. There are options that relate to this complete process on the Common Options page of the PowerFlow Solution Options and Simulator, and you can see where all of those are identified and pointed to here. Here is our inner PowerFlow loop, and here are the options related to the inner power flow loop. We have the convergence tolerance, maximum number of iterations, and the do only one iteration is not really used here other than educational purposes, where it does one iteration at a time. But it is important to note what the convergence tolerance and the maximum number of iterations are. And then for the middle loop, the controller loop, there are options related to that as well. You can disable switch shunt control, which turns off step 4. You can disable SVC control, which turns off step 5. You can disable LTC transformer and phase shifter controls, which turns off step 6. Or you can disable DFACs control, which turns off step 7. And then generator MVAR limit checking, again, note that there is the check immediately and check back off immediately options up here that would move this limit VAR checking up here into the inner loop and do it before it actually solves the power flow. But keep in mind then that it's checking it every time it solves the power flow, instead of only checking it each time the power flow is solved and it comes out back out to the middle loop. So that's why it can slow it down. Then there's also down here the maximum number of control loop iterations that you can specify, so it will repeat until no more switching is detected or until this number of iterations is reached. As I mentioned, there is an option to prevent controller oscillations. Typically you want that checked. That option is right here, as well as the transformer stepping methodology right here that it uses in step 6. So there is the option for coordinated sensitivities or self-sensitivity only. This is an example of the message log for a solution. We've tried to color code this so that as you see the messages in the log, you can tell what part of the solution process those messages are being provided from. So for example, the inner power flow is here, and those messages are reported in black, and I can see that it's showing me what the steps of the Newton-Raphson solution are and how it's converging to a solution within tolerance and where my largest mismatches are in terms of what bus they occur at. The generator VAR limit checking is kind of this darker purple color, so this is where it's checking generator VARs here. This black also as well is a DC line flow adjustment. You can see that, for example, here it's doing a DC line flow change. This orange color, switch shunt control. Green is where it's changing taps on transformers. This brighter pink color, it's changing phase on phase shifting transformers. And all of these colors that you see here are adjustable or customizable by you. So you can go into the simulator options and go to the message log options, and you can specify how things are reported in the log, what color coding is used to report those messages to the log, or you can have it suppress messages of certain types and not have it display them. And we do this because obviously some people are colorblind. They see certain colors and not others. So if there's colors that we use by default that are not discernible by the user, they can adjust these colors here so that they can tell the difference between these different message colors in the log. Here's just another follow-up of that log, so you can see where it's doing more inner power flow loops and more checking of generator VAR limits, and other inner power flow loops, more tap changes, another switch shunt that adjusted. This blue color here is automatic generation control iteration taking place. So after it has done several middle voltage control loops, it was satisfied with no more voltage control changes, so it went back out to the outer loop and did another generation adjustment, and then came back in and did another inner power flow loop, another adjustment of transformers, another inner power flow loop, did a calculation of adjustments to transformers and didn't adjust any. It didn't do any other adjustment. It didn't have to do any more generation adjustment, so it finished. Okay, so the log can be very helpful with the color coding for you discerning where during the process of the outer, the middle, and the inner loop things are going on. How many inner loops did it do? How many times did it go through and solve the Newton-Raphson? How many times did it adjust transformer taps or switch shunt settings and so on? How many times did it adjust the generation output? So you can get all of that out of the log. So let's talk about now some advanced options for the power flow solution. So we've talked about how the power flow is solved and all the various parts to that solution that go on and occur. So let's talk about some advanced options that can affect how that power flow solution is solved. So we've looked at the common options before, which relate directly to those outer, middle, and inner loops that we talked about, as well as the pre-processing steps. Now let's talk about some advanced options here. And you can get to the advanced options by going to Simulator Options on the ribbon, or you can go to the Simulator Options button on the Quick Access toolbar at the top. And once you open that up, it's going to come up to the Common Options. The second tab is Advanced Options, and you can reach those options here. The Advanced Options tab has several things on it. First of all, there's an option to dynamically add or remove slack buses as the topology is changed. What this does is it allows you to solve multiple electrical islands if you have this checked. If a single island is split into two islands by opening lines during the course of your solution, then Simulator will, if allowed, dynamically select a new slack bus in the part of the island that was separated from the designated system slack. It's usually the generator with the largest megawatt limit that regulates its own terminal bus, and it will be selected as a slack to use for solving that new electrical island, separate from the original. There's also an option for the post-power flow solution actions, which allows you to define a list of conditional actions, much like a contingency definition, which occur at the end of every power flow solution. So if there's something that you want to be evaluated at the end of every solution, and perhaps a line, for example, that you want to be opened if the flow exceeds a certain amount, you could have a power flow solution action defined that says if the flow on line X exceeds 50 MVA or 100 MVA or 500 MVA, that it will automatically open that line and resolve the power flow for that condition. There's also, for example, if loads should automatically be taken out of service when voltage drops too low. That's probably more realistic use of it. But it's basically like you're applying an automatic contingency condition, but you're doing it to every power flow solution that you solve. And you're going to check something, some condition, and if that condition is met, you're then going to do something else and resolve it. So that's what you would see here with these post-power flow solution actions. Some other additional advanced options on here. You can disable the power flow optimal multiplier. The optimal multiplier is a mathematically calculated step size for Newton's method. It prevents the mismatch equations from increasing between iterations. The advantage of the calculated step size is that it will converge a little quicker. The disadvantage on occasion for the optimal multiplier is there are occasionally situations where the load flow will fail to converge because of the optimal multiplier. And it typically happens in a case where the circumstance of your solution is that you're reaching a minima on your solution curve where the slope of the curve is very, very flat. And in that situation, you basically have a really wide parabolic shape at the bottom of where you're trying to find the minima, and the optimal multiplier tries to find the best step size to move from wherever it is on the curve now to the minima. But because the slope of that shape is so flat, when it takes a derivative of it to find the step size, it actually ends up being a very large step size because you've got a very flat curve. And so it actually ends up overshooting the solution and going to the other side of the curve. And then it calculates the value again of the optimal multiplier on the other side of the curve and calculates another big jump back to the other side. And you'll actually find where the optimal multiplier causes the solution to bounce back and forth to either side of the local minima without actually finding it. If you turn that off, then it just uses a fixed step size and just marches its way by fixed step size down to the minima until it reaches close to the minimum point. Most of the time, the optimal multiplier works great and gets you close to your local minima just fine, as long as the shape of your curve at that point is not a really flat curve. But in rare situations where it is a really flat curve, you sometimes have to turn off that optimal multiplier in order for Newton-Raphson to actually solve. So that's why we gave you the option to disable that. There's also an option to initialize from flat start values. This always starts the power flow solution with voltages and angles set to specific values. The generator buses or buses regulated by a generator are set to the set point voltage of the generator. And then it's set to 1 per unit for all other buses. And then it sets the angles equal to the slack bus angle. And then we say we don't recommend this. That is true. We don't recommend it for a realistic load flow model or a model of your actual transmission system because setting it to a flat start is such a drastic difference in starting point for the Newton-Raphson load flow that we typically actually call it a bad starting point or an ill-conditioned starting point for the Newton-Raphson because it's so far away from what you would actually have for your voltage and angle solutions all over the system that Newton-Raphson just can't find a solution for it. Flat starts work okay in small systems, little study systems, or if you've taken a large chunk of your system and you've extracted a small piece of it and you're solving it, as a small piece of the system, a flat start might work okay for that. But for a large system with thousands of buses and transmission lines, trying to use a flat start just doesn't work. There's also an option for the minimum per unit voltage for constant power loads and constant current loads that you can set. You can see that here. At voltages less than the defined values, the constant power and constant current loads will be reduced. To disable either of these features, you just set the value to 0 and it won't do it. But the intention is that if the voltage or the voltage starts falling below these thresholds, then we do adjustments of the load values of constant power or constant current loads to try and keep the solution solvable by allowing the values of the load to be reduced at those points so that the voltage isn't falling as fast. We can talk about that a little bit more. So when a bus voltage is below either of these two thresholds, the constant power or constant current load will gradually decrease to 0 megawatts at 0 voltage. So constant power loads will use a cosine function to reduce. Constant current loads will use a sine function multiplied by the voltage to reduce. The functions are chosen so that the derivative of the load with respect to the voltage is continuous, because we don't want any discrete changes in those derivatives or we will have a failure of the load flow. So here's what you can see, for example, here. So if the voltage falls below the constant power threshold that we define, then we use a minimum per unit voltage for constant power that's a cosine function so that the derivative with respect to voltage remains continuous. And then for a constant current load, we use a sine function multiplied by the voltage so that the power reduces as well, so that as it reaches 0 voltage, we would hit 0 load. So it's just a way to try to massage the loads down to maintain a load flow solution and allow the power to be reduced rather than stay constant, or to reduce at a different rate rather than a constant rate for constant current. Okay, so some other options on the Power Flow Advanced Options tab. You can disable treating continuous switch shunts as PV buses. Continuous switch shunts are normally treated as buses with fixed real power and voltage inside the inner power flow loop. But if you choose to instead disable them from treating them that way, then you can do that and it will treat them as switch shunts in the middle control loop instead. You can disable balancing parallel LTC taps. Typically, we don't advise that. Parallel LTC taps normally have their tap values synchronized to prevent circulating VAR flow. That's a good thing. You don't want to have a large amount of VARs circulating on parallel transformers because their taps don't coordinate. So we have options that by default we balance those parallel LTC taps. If for some odd reason you want to turn that off and allow there to be circulating VARs on the transformers, you have that capability, but we don't advise it. You can also model phase shifters as discrete controls. By default, they are typically treated as continuous control devices during the course of the load flow for simplicity. But in reality, phase shifters actually switch tap positions discretely based on their tap step size, which is an angle step size. We don't normally model them that way because it can slow down the power flow solution, but you have the ability to choose to do that if you wish. You can also disable transformer tap controls if tap sensitivity is the wrong sign. Normally we do want that. If a transformer is regulating one of its own terminals, the voltage to tap sensitivity should be positive if it's regulating the from bus and negative if it's regulating the to bus. If the sensitivity has the wrong sign, it indicates an unusual system condition, and if you allow it to continue, it will actually drive the voltage in the wrong direction. So that's why you want to typically disable transformer tap controls if the sensitivity has the wrong sign. There's also a minimum sensitivity for tap control, and if a transformer has a sensitivity lower than that amount, it just gets turned off and does not try to regulate because the change in voltage is so small for the change in tap that it will take numerous iterations, if it even finds the solution at all, that the transformer can satisfy the voltage at that point. So you have the ability to specify a minimum sensitivity for transformer control change. So here's a discussion of some of these other options. For example, the parallel tap balancing and minimum tap sensitivity. For an example here, there's a case that if you open it up, it's called advancedoptions.raw. If you open it up and you look at it before it's solved, I'm just going to do it here on the slides. I'm not going to actually open the case. But there's a custom view where we're going to specify loading a file. You can load a custom view from a file, and it loads busviewtaps.aux, and it chooses transformer taps. So we can say we want to choose the transformer tap view that was saved previously in this busviewtaps.aux file, and then we can switch to that custom bus view. So that switches to a custom bus view which set up some tap values in the bus view one-line diagrams so that we can see what the taps are right here of these four parallel transformers, and we can note that they are not balanced right now. We have two that are the same and the other two are different, which means right now there would be circulating VARs on these transformers because of the difference in taps. And parallel transformers, if possible, should have the same tap ratios so that the VAR flows are all constant in terms of they're all roughly the same VAR flow on each transformer, all flowing into one of the two terminal buses, not that we have a circulation of VARs. So if we look at a different bus in this example, we'll see at this bus we have two transformers regulating the same bus, but they have different regulation ranges. So again, we want parallel taps to balance the flows and avoid circulating VARs, but what do we do about the case of having different control ranges? Well, what simulator does is it uses the intersection of these ranges as the ultimate control range for these transformers. Because if we want to keep them balanced, that means we want to try and keep the taps of the two transformers operating at the same value. And in order to do that, we have to reduce the control range to be the intersection of the two control ranges of the transformers so that the two transformers can stay balanced. If there's no intersection of control range, then we turn the control off, because that means the two transformers would be fighting each other constantly for control of the voltage at the regulated bus. So here's another check of parallel transformer taps. In this sample case, does not have this problem, but we have, the slide is just setting up an example. We have parallel transformer taps which do not have the same regulated bus. This one is regulating 56,649. This one is regulating 55,649. In this case, the transformer will be turned off control if this occurs, and a log message will be displayed telling you that the following parallel transformers do not share the same regulated bus. So we will turn these two off of control, because this is a situation that just cannot be satisfactorily handled by the load flow, because these two would be fighting each other constantly to regulate the voltage at two different buses. One's regulating over here and one's regulating over here. We also allow control if the regulated buses are within a group of buses connected by a very low impedance branch. What that means is if there was another branch here that was low impedance connecting these, then we would allow that control, because in theory these two buses should have the same voltage. So that would be all right, but typically that doesn't happen, and if we find this situation, we just turn off the control for these two transformers. Here's a minimum tap sensitivity example. In this case, because the generator at bus 51039, which is down here, controls the voltage at bus 51040 over here, the two transformer taps will not be able to regulate their voltages. In this case, this transformer is trying to regulate 51050 here. This one is trying to regulate 51040 here. But this generator is already regulating this voltage, and it crosses both regulated buses of these two transformers. So in this case, taps are only useful when the generator is at its VAR limit. Otherwise, these taps will not adjust, because this generator is going to be regulating this voltage directly anyway. We're trying to give you a whole bunch of different scenarios when there are situations where transformers will not regulate for one reason or another, and we've tried to incorporate all of these different situations into the simulator so that simulator handles these as smartly as it can. So what does simulator do with these examples that I've talked about? So if I go back to slide 27, this is Rector. This situation, we had 4 transformers in parallel that had different taps. Slide 28, at Shell, we had the situation of 2 transformers that had overlapping regulation. And then here we had 2 transformers that were regulating different buses. Again, this was just an example that's not in there. But at slide 30, we had the situation of these 2 transformers regulating these 2 buses, but the generator here also regulating this bus over here. So how does that translate to the log? Well, in the case of Rector with the 4 parallel transformers, it tells me that it had to adjust the tap ratio of these transformers to balance those parallel LTCs. So it has adjusted the taps to balance them. At Shell, it tells me that the following transformers have control ranges that are not the same. So it tells me what the regulation range is that's being used, and then it's the intersection of those ranges, and then what the ultimate solution of those transformers was. And then in the last case of ICG, it tells me these 2 transformers cannot regulate or control their voltage effectively, and that it will ignore those until the tap sensitivity magnitude increases. So that's what these transformer taps are being adjusted for, and the reason the sensitivity is so small that they can't effectively control voltage is because the generator is already controlling it. So when it calculates the sensitivity of these transformers to regulating their terminals, it's going to come up with basically 0, because the generator is controlling the voltage instead. So some other options on the Advanced Power Flow Solution page. You can disable the angle rotation processing. This is a pre-processing step. Voltage angles are rotated so that the angle range in an island is equally spaced around 0 degrees. If any angles fall outside of plus or minus 160 degrees, you can turn that off, but it might cause solution problems if your angles start getting that far apart. You can disable angle smoothing. The solution difficulties can result if branches are closed with large angle differences across them, and angle smoothing helps reconcile those differences. So again, if you disable that, you might be lending yourself to some solution problems if you're closing in any long lines or multi-section lines. There's sharing of generator VARs across groups of buses. You can allocate across buses using the user-specified remote regulation percentages, which is the normal operation we've talked about. But there's other options here as well where you can allocate so all generators are at the same relative point in their min or max VAR range. So that's an option that you have for VAR sharing of generators. You can also allocate across buses using the sum of user-specified remote regulation percentages instead of using the user-specified actual values. And then there's also what we call a ZBR threshold here, which we don't talk about, but this is just at what point do you consider a branch a zero impedance branch? And so you can say if the impedance is below 0.0002, we call that zero impedance branch. The only reason that becomes important is there are some zero impedance branch handling things that go on internally in the software if it's designated or determined to be a zero impedance branch. If you make this number larger, you're going to have more small impedance branches that are used in various calculations internally in the software. The more that are used, the longer it can take, and the more possibility there is for a solution failure if you have a whole lot of low impedance branches that you're including in various aspects of the solution process. And this talks about what that ZBR threshold is. It determines which buses will be considered the same because they are connected by low impedance branches. This affects things like generator and switch shunt regulation, parallel transformer tap balancing, and voltage preprocessing. There are also options for areas on economic dispatch. Economic dispatch does not really get used very often in simulator anymore. Typically, if someone is going to solve looking for LMPs, for example, they're going to do an OPF. They're not going to do an economic dispatch because economic dispatch ignores line flows and constraints on lines, whereas the OPF includes them. But if you do choose to do an economic dispatch where it just solves the generation, minimizing cost, you can include loss penalty factors in the economic dispatch, which will consider losses in determining the dispatch. So that's what this option is here. You can also enforce convex cost curves in the economic dispatch, which will turn units that are operating outside the convex portion of their cost curve off of automatic control. So again, those don't get used very often, but those options are there. Sharing of generator VARs across a group of buses. On this example, we have generators at 4 different buses: 62047, 62048, 62049, and 62050. So these two and these two here. They're all regulating the voltage at this bus, 62057. If you look at these 4 generators, we have currently them set to allocate across buses using their user-specified remote regulation percentages. So the present setting is to allocate using these regulation percentages designated here. So you'll see 35, 35, 15, and 15. And so the generator megavar outputs that are shown here reflect these percentages. So these are following these percentages directly, and the sum is 347.68 megavars. If we instead model or modify the value of the min megavar and max megavar, the gen megavar values will not change. So if we change this from 270 as it was here to 150 as it was here, it doesn't have any effect on the solution. There's no change in megavar outputs because it's allocating it directly based on the user-specified remote regulation percentage. So 121 is still below 150, so it doesn't care. If we change this back to its original 270.7 megavar limit, and now we go into the options dialog and we change the advanced option to allocate so that all generators are at the same relative point in their min and max var range, and do a single solution, we don't get a change. And the reason is because those 35 and 15% change, 35% and 15% actually come from the VAR range ratio that we currently had between the max of these two and the max of these two. But if we see a different behavior, or to see a different behavior, we can change the min megavar and max megavar, for example. So if we change the max megavar of this generator from 270 to 150 and do a single solution, we notice that all these values change. And they change because simulator calculates the constant ratio based on what the max megavar is minus the min megavar. So here you'll see for the first one we have max minus min for the denominator, and then its actual minus min has to meet a constant ratio of 0.789. So for this 0.789 ratio, we end up with new values of VAR output for all the generators because we changed the max value of this generator here. So all we've done here is we've changed the type of control from using the absolute value of the remote regulation percentage provided to instead using the ratio of the max megavar minus min megavar for controlling the generator voltage. And note that the sum here should still be the same as we had before. It's just that we've got one that is reduced because of the change in voltage, or the change in maximum VAR level here. So now if we talk about switch shunt specific features, each switch shunt has an option to allow it to switch during the inner power flow loop. This allows discrete switch shunts to be treated as PV buses initially and then revert back to discrete shunts after the initial solution. Reverting back to discrete shunts is done in step 1A of the overall power flow solution process. This will cause the additional inner power flow loop iterations. So if we allow switching in the inner power flow loop, we'll end up with more iterations of the Newton-Raphson load flow, and it might take a little longer to solve. There's transformer-specific features as well. With each transformer, a field called regulation range target type is available. You can choose to either have it target the middle of the regulation voltage range or to just target the max or the min. And what this does is it determines what the target for the transformer control is when it's not meeting its regulation range. If you say middle, it might have to switch more taps on the transformer to try and hit the middle of the range. If you say just go to the max or min, then if the voltage is found to be violating either high or low, it just determines how many taps to adjust on the transformer to get it back to that minimum or maximum. So it's just a little bit of a variation in what you want the transformer to do as it regulates voltage. So let's talk about area control with multiple islands. When an area spans multiple electrical islands, the megawatt interchange control for that area may not be possible. An error check is done to allow for more complex situations. So an area that belongs to multiple islands can be placed on control only if at most one of these islands contains multiple areas. Gets a little confusing to think about, but we try to graphically illustrate it. So here, area spanning multiple islands, an example for area number 1 control. So we have area 1 over here, which has island A and island B and part of island C. Control is allowed because only island C spans multiple areas. Island B and island A do not. However, over here, control is not allowed because island A and island C both span multiple areas. And in this situation, it's just impossible to figure out what the correct dispatch of generation should be in each of these islands across these different areas in order to maintain the correct area interchange. Why is control not allowed in this situation? It's not allowed because we don't have enough information to know which generators should respond when transactions are specified. So if area 1 and area 2 have a transfer between them, should the transfer occur in island A or in island C? We don't know, so we can't control that. There's some other solution diagnosis aids. Displays for showing which devices remotely regulate a particular bus are available. So generators, LTCs, and shunts. It appears on the run mode bus dialog. and on the Model Explorer under Solution Details, Remotely Regulated Buses display. So over here you can see if you're looking at a specific information dialog for a bus, it will tell you down here what devices are regulating the voltage at that bus. So you can get that. If this is blank, then that bus is not having its voltage regulated. You can also see that information in the Remotely Regulated Buses table, which is under Solution Details in the Model Explorer. If you click on Remotely Regulated Buses, it will list a bus that is being remotely regulated, and it will tell you what devices are remotely regulating it. So in this example, it will list the remotely regulating generators here. If you were to expand this out, you would see a list of more, and it also lists them out here as well. So you'll see the list of generators that are regulating the voltage at this bus. And it tells you what the total megavar is coming from these 4 devices in order to regulate the voltage at its set point of 1.08. So this is just a tabular display showing you all the buses that are being remotely regulated by which devices and to what value. There's also a field for buses called solution type, which is going to tell you if the bus is a PV, a PQ, or a slack bus, or some other form of bus. There's some other types as well. These are descriptive strings to better help understand the power flow solution. And the column is shown by default on the network mismatches table. So again, if you go to the Model Explorer and go to Solution Details and click on Mismatches, you will get a listing of the buses and what the mismatches are at each bus. If it's a solved power flow, they should be 0 or very close to 0. And it will also tell you what type each bus is. Is it a PQ bus? Is it a PV bus that is a remote regulation master? Or is it a PQ bus that's a remote regulation slave? Okay, so it tries to tell you that what generators are being remotely regulated, or what buses rather are being remotely regulated, what buses have a generator that are remotely regulating something else. So it's a PV bus because it's remotely regulating somewhere, so it's a master, or a remotely regulated slave. This is a bus that's being remotely regulated, or is a PQ bus because it's remotely regulating something else. So we have these fields, and you would see if it was a slack bus, it would say slack. So that would also be listed for the slack bus. If you have multiple islands, you would see more than one listed as a slack, because each island, as long as it's dynamically being allowed to solve, would have a separate slack for the solution. You can also look at the zero impedance branch groupings display, which is under Solution Details and Bus Zero Impedance Branch Group. So what this tells you is that you have a master or controlling or a target bus that is part of the group. In this case, it's 74001, but it is actually the primary bus for a ZBR bus group, and it tells you which buses are included in that group. So we have bus 74001 and 74003 are connected by a zero impedance or ZBR branch. What determines a branch as ZBR is based on that parameter that we discussed earlier in the options, that you set a impedance threshold as to when a branch is considered a ZBR or not, and that directly impacts what it sets as these ZBR groupings. If a branch has an impedance above the ZBR threshold, it will not be treated as a ZBR, and you would not see them grouped together as such. So this is listing the primary for each group and then all of the buses in the group. So it just gives you a little bit of information about ZBRs. There's also some island information. There's an island information dialog which lists the buses, generators, loads, and switch shunts that are part of an island. So if you go to the island information dialog, you will see that you can pull up a table of all of the buses in the island, all the generators in the island, all the loads, and all the switch shunts. So you can figure out what devices are in each electrical island if you have multiple electrical islands in your case. And this is useful if you're choosing to solve all of your islands separately, if you have multiple electrical islands, and you're interested in knowing what parts of your system fall inside which electrical island.
If you need further assistance, please feel free to look us up on the web, give us a call, send email to our support line, or if you prefer to work with a particular Power World engineer, please feel free to contact that person directly.